Hi! The Milky Way galaxy is our home and it's a vast, sprawling metropolis of stars, gas, and dust. With billions of stars and potentially habitable planets, it's a cosmic wonder that continues to captivate astronomers and space enthusiasts alike. On this channel, we have already talked about the stars, dust, and gas, the individual components that make up a galaxy. In this episode, we'll explore all these components and their distribution which lead to the characteristics of our own Milky Way. Let's begin. According to the Greek mythology, the queen of gods Hera spilled her milk while breastfeeding an illegitimate child of her husband and king of gods Zeus. According to the legend, this baby, called Hercules, had been placed on her chest to gain superhuman powers while she was asleep. And so when she woke up and realized who she was breastfeeding, she pushed the baby away and in the process spilled her milk, or galaxias in Greek, across the sky, which makes the Milky Way. It is therefore not surprising that the dark band which we call the Milky Way when observing from Earth looks like the spilled milk across the sky. However, the Hindi and Sanskrit name of Milky Way is Akash Ganga, which literally translates to the Ganges of the sky. But as Shakespeare said, what's in a name? As we'll see in a few minutes, the Milky Way appears to us as it does because of the fact that we are in the disk of the galaxy itself. But before we proceed, recall that star clusters can be classified into two categories: open and globular clusters. The open clusters contain a few hundred to thousand stars, are less than 10 parsecs across, and are found in the plane of the galaxy's disk. Open clusters are young, that is, have young stars and therefore may contain dust and gas produced during star formation. The globular clusters, on the other hand, contain 10 to 100,000 stars, are much larger, about 20 to 100 parsec in diameter, and are located outside the galaxy. Globular clusters are very old and hence contain little or no gas and dust. But there is another important difference between the stars in the open cluster and the globular clusters. This concerns with the abundance of metals in these stars. In astronomy, metals refer to the elements which are heavier than hydrogen and helium. Many globular clusters have stars with very low metal abundance, while open clusters are higher in metals. These high metal stars are called population 1 stars, and the low metal stars are consecutively referred to as the population 2 stars. A general sense is that population 1 stars are younger, more recently formed stars. The metal abundance difference is interpreted as reflecting the conditions in our galaxy when each of these stellar populations formed. When the older stars formed, our galaxy only had hydrogen and helium, but when the new stars formed, the gas in the galaxy had been enriched in metals. The enriched material came from the nuclear processing in stars, which spread out the heavier elements in the interstellar medium through stellar explosions towards the end of the life cycles of massive stars, as we have discussed in an earlier video. This means that the globular clusters are old, and long time ago star formation in our galaxy happened in a spherical volume. But the open clusters, also known as galactic clusters, are younger and formed in the disk much later on. The population 2 stars found in globular clusters are associated with the old component of the galaxy. Their spherical distribution is known as the halo. But note that the density of stars in the halo falls off with the distance from the center of the galaxy. These population 2 stars also have a larger spread in their velocity distribution relative to the population 1 stars. The first evidence of our true position inside the galaxy came from the work of Harlow Shapley, who studied the distribution of globular clusters. Shapley found the distance to the clusters from observations of Cepheids and RR Lyrae stars, which we have discussed in our video on distance measurements in the universe. Shapley found that the globular clusters form a spherical distribution with the center around 10 kiloparsec from the Sun. Presumably, this is where the center of the galaxy must lie. Based on the data accumulated so far, since the year 1985, this distance has been modified to 8.5 kiloparsec by the International Astronomical Union. The schematic arrangement of various components of the galaxy are shown in the image here. The center of the galaxy is surrounded by a bulge. The halo has a spherical distribution with the density of material that falls off radially. The disk looks like a dinner plate from overhead, and the Sun is placed around 8.5 kiloparsec from the galactic center, about halfway out to the edge of the disk as seen in the side view. The inner part of the disk, which is closer to the center than the Sun, is thin and flat, but in the outer part, the disk is relatively warped and gets thicker. That is, it flares out. The multi-wavelength images of the disk of the galaxy shows the distribution of different components therein. Each image represents a 360-degree false color view of the Milky Way within 10 degrees of the galactic plane. The images are in galactic coordinates, which we'll discuss in a few minutes, with the direction of the galactic center in the center of each panel. For scale, the vertical dimension of each image is about 40 times the angular diameter of the full moon on the sky. The image shows the Milky Way disk in the radio at a frequency of 408 MHz all the way to greater than 10 to the power 13 GHz in the gamma rays, revealing the different components and their distribution in the disk of our galaxy. All the material in the galaxy orbits the galactic center. If our galaxy was a rigid body, all the material would orbit with the same time period. But that is not the case. Materials closer to the center orbit with a shorter period relative to the outer stuff. This is not unusual because, for instance, the planets in the solar system exhibit the same behavior. Mercury, for instance, has a shorter time period around the Sun than the Earth, and so on. This type of motion, where the orbital velocity depends on the distance of the material from the center, is called differential rotation. The orbital period of any particle will depend upon the mass about which it is orbiting and the radius of that orbit. Just like we can use the orbital period and size of the Earth's orbit to estimate the mass of the Sun, it is possible to use the orbital periods at different distances to learn about the distribution of mass in the galaxy. For a spherical mass distribution, the motion of an object at r depends only on the mass contained within that radius r. The mass m of r behaves as if all of it is concentrated at the center. Therefore, if we assume that all matter follows circular orbits, at a distance r from the center, the orbital speed given by v of r and the angular speed given by omega of r, the mass interior to the radius can be given as an integral of rho over r dv going from the limits of 0 to r, where rho of r is the density at radius r and dv is the volume. For a particle of mass small m orbiting at a radius capital R, the gravitational force is given by gmm by r square, and this must provide the acceleration for the circular motion. So by equating the two forces, we can get mass as a function of velocity and radius given as m of r is equal to v square r by g, where g is the gravitational constant. But if we assume that all the mass is concentrated at the center of the galaxy, capital M by r is a constant, which implies that this equation gives Kepler's third law, and the orbit of the object in such a case is known as Keplerian. This means if we can measure v of r, we can actually estimate the mass within that radius r. The function v of r, or omega of r, is known as the rotation curve of the galaxy. The differential galactic rotation produces Doppler shift in spectral lines that we observe from gas at different distances from the center than the Sun. Let's understand this with a little demonstration. Consider 5 test particles at different distances along a line of sight. In each case, the Doppler shift depends on the relative radial velocity of the particle and the sun. To do this, we take the line of sight component of the particle's motion and subtract the line of sight component of the sun's motion from it. As we see, particle 1 is slightly closer to the center of the galaxy than the sun. It is moving slightly faster than we are, so there will be a small Doppler shift. Since it is moving away from us, so the shift will be towards the longer wavelength, that is, the object is redshifted. Our line of sight crosses the same circle at particle 2. So the speed is same as particle 1 and the angle with the line of sight is the negative of that at particle 1. Since the line of sight component depends on the cosine of that angle, that component is also same. So the Doppler shift for particle 2 is same as that of particle 1. Now the line of sight passes closest to the center for particle 3. The material is moving fastest around that circle. Since it is also moving directly away from us, that point has the largest Doppler shift towards the red. Particle 4 is the same orbit as the sun. Our distance from that object remains constant, so our relative velocity must be 0, meaning that the Doppler shift for this particle is 0. Particle 5 is farther from the center than the sun and is moving slower than us. Therefore, we are overtaking it and imparting it a Doppler shift towards shorter wavelength, which means it appears blue shifted. In determining the rotation curve for our galaxy, it is therefore convenient to introduce a set of coordinates known as the galactic coordinates measured from our viewing point in the solar system as shown in this image. Here, the galactic latitude b measures the angle above or below the galactic plane of an object. You can think of it like the two hemispheres dividing the Earth at its equator. The galactic longitude L is an angle measured around the galactic plane starting in the direction of the galactic center. We also define a convenient frame of reference for measuring the velocities. This is called the local standard of rest or LSR. If the only motion the sun had was its orbital motion around the galactic center, the local standard of rest would coincide with the sun's motion, which means we could in that case simply measure the motion with respect to the sun. This is what is known as the heliocentric velocity. However, since gravitational interactions with the neighboring stars and other objects are also playing an important role, the sun has a small motion superimposed on its circular orbital motion. Therefore, it is not a convenient reference point to measure velocities. Now, data has been used to estimate that at a distance of 8.5 kiloparsec from the center, the sun goes around it at a velocity of 220 kilometers per second. As shown here, we can use this to estimate the time it takes for the sun to orbit the galactic center and the mass which is interior to the sun's orbit. To calculate the time taken by the sun to orbit is simply its circumference 2 pi r naught divided by the speed v naught. This tells us that the sun takes 240 million years to orbit the galactic center. As shown in the second calculation, the mass interior to the sun's orbit can be calculated as m is equal to v naught square r naught by g, which is what we just derived. And this yields a mass of 100 billion solar masses for the Milky Way within the sun's orbit. From what we have learned so far, the rotation curve for material within the sun's orbit can be determined reasonably well from the 21 centimeter line observations. To do so, we only have to make two important assumptions. Number one, the orbits are circular, which means that we will have to measure the velocity at only one point for each value of r. And number two, that there is some atomic hydrogen all along any given line of sight. This method takes advantage of the fact that for lines of sight through any part of the galaxy's interior to the sun's orbit, there is a maximum Doppler shift. It is easy to check the 21 centimeter spectrum at each longitude and determine the maximum Doppler shift. We can then assign that Doppler shift to the material at the point of closest approach to the galactic center for that particular longitude. With longitudes ranging from 0 to 90 degrees, the corresponding value of R minimum will range from 0 to R naught, which is the radius of the Sun from the galactic center at 8.5 kiloparsec. Such a rotation curve for the Milky Way is shown in this image, where the 21 centimeter data is used to get the curve inside the Sun's orbit, while molecular clouds in the H2 regions are used outside the Sun's orbit. The spectroscopic parallax on the exciting stars is used to measure the distance to the H2 regions, and then CO observations are used for measuring the Doppler shift. Do check out our earlier videos on the distance measurement in the universe and 21 centimeter observations for more details. This rotation curve shows that out to 20 kiloparsec from the center of the galaxy, there is no decline in mass outside the Sun's orbit, unlike what was previously assumed. Remember, this is the total mass that we are talking about. But from the data, it is obvious that the brightness of our galaxy falls off as radius increases. Since the luminous part of the matter is mostly in the disk, it seems that this extra mass cannot be part of the disk. Current understanding is that this extra mass is in the halo of the galaxy. We still have little idea of what form this matter takes. It has, however, been suggested that this can be in the form of faint red stars, but recent results make this very unlikely. This is our first encounter with dark matter, a form of matter whose gravitational effects can be felt, but it is not luminous and hence cannot be seen. Please refer to our earlier videos on the dark matter for a detailed discussion on this topic. Coming to the gas in the Milky Way, note that the amount of H1 at any radius is only about 1% of the total mass within that radius. The amount of H1 does not fall off quickly with radius. The mass of H1 inside the Sun's orbit is about 1 billion solar masses, while outside of its orbit is twice that amount. Inside the Sun's orbit, the mass of molecular hydrogen is approximately same as that of atomic hydrogen, but outside the Sun's orbit, it is just about a quarter of that. The distribution of molecular hydrogen peaks at a distance of around 6 kiloparsec from the galactic center. This is a site of intense star formation and is popularly known as the central molecular ring or central molecular zone. At the position of the Sun, the thickness of the disk is around 300 parsec, but at a distance of 15 kiloparsec from the center, the thickness is 1 kiloparsec. This implies that the plane of the disk becomes thicker as one goes farther out from the center of the galaxy. This is called the flaring of the galactic disk. In addition, we also note that the disk is not flat but has a warp to it, just like the brim of a hat. The warp is most prominent outside the Sun's orbit. The bend is upwards in the first and second quadrant of the galaxy and downwards in the third and fourth quadrant. While many galaxies in the universe are spirals, from our position inside the disk, it is very difficult to observe the overall pattern of our own galaxy. However, based on the data, we can detect certain similarities between our galaxy and other spirals that we observe. For instance, most spiral galaxies have a significant amount of gas and dust comparable to what we observe in our own Milky Way. We also note that the spiral arms are not continuous bands of light, but appear to contain knots of bright stars and glowing gas. Similarly, when we observe the H2 regions and OB associations in our own galaxy, they seem to trace out the spiral arms just like in other spirals. Therefore, astronomers like to study the patterns created by the H2 regions observable in our own galaxy. Of course, a drawback of this study is that with the optical data alone, we cannot look very far along the plane of galaxy because of the dust present there. In this scenario, the radio observations come to our rescue and allow us to observe the whole galaxy on a larger scale. By utilizing the kinematic distances, astronomers estimate the interstellar gas and spiral structure by using the 21 centimeter line and have identified several long connected features similar to spiral arms. The galactic center has been a tantalizing topic for astronomers since the discovery that we are not at the center of the Milky Way. When we talk about the central region, we basically mean the inner 500 parsecs of the galaxy. Visual extinction in the galactic plane makes the optical studies almost impossible. Therefore, the galactic center is mostly observed in the radio and infrared wavelengths. In radio, astronomers have detected continuum emission from ionized gas and line emission from molecular clouds. In the infrared, the continuum observations tell us about the dust temperature and opacity, and spectral line observations tell us about the neutral and ionized gas present there. Near-infrared observations have been used to study the star clusters near the center. Now, the galactic center has also been mapped in X-ray emission. The molecular material in the inner 200 parsec is remarkably hot and dense relative to the giant molecular clouds elsewhere in the galaxy. Typically, the temperatures are 70 K and the density is greater than 10,000 per centimeter cube. While these conditions in a normal molecular cloud are present only in the core, in this case, such conditions prevail over the full extent of the cloud. The molecular material may be as high as 100 million solar masses. The galactic center therefore provides a very unique environment for star formation. There is high density of gas, but it is inhibited by high temperature, velocity dispersion, magnetic pressure, and tidal effects as well. Also, observations show us that the central parsec is very rich in past and current star formation. The star formation rate in the central region is estimated to be as high as 1 solar mass per year. The central star cluster shows evidence for a new 10,000 solar mass burst superimposed on an older 1 million solar mass cluster. There have been suggestions that the formation of the newer cluster triggered the formation of at least 2 other rich nearby clusters as well. The source in the center of our galaxy has been named Sagittarius A star. In order to determine the properties of this central source, researchers at the UCLA observed it at a wavelength of 2.2 micron with a very good angular resolution and identified 90 stars whose motions could be tracked. Assuming that the central source is a black hole, note that while the proper motions for other stars are usually very small to measure over a period of a few years, in the vicinity of a massive object such as a supermassive black hole, the stars should move very fast, thereby producing measurable proper motions. In fact, the largest proper motion corresponded to a tangential velocity of 1400 kilometers per second. Astronomers found that this motion is around the position of Sagittarius A star, and projected position and velocity of stars are consistent with Keplerian motions. This implies that essentially all the mass is closer to the center of the galaxy than any of the stars which were measured. The best estimate of the mass in the central object is around 4.2 million solar masses. I hope you learned something new about our own Milky Way today. Do share your suggestions and let us know what other topics you would like to be covered on this channel. We look forward to your feedback, and if you like our videos, do share our content with other astronomy enthusiasts. I will see you next week. Until then, take care.